Hi everyone. My name is George Barnett and I'm a software engineer at Apple, where for the past 6 years I've been working on Swift on Server in the services engineering org. Today, I'm going to talk to you about building a new gRPC library in Swift. For existing gRPC users, I hope to give you a taste of our new library and an understanding of why we think Swift is a great language, particularly for server development. For library developers and maintainers, I hope you'll take away some of the things that we learned while going through this process. I'm going to start with why we're interested in Swift and what makes it a compelling language choice. Swift is a modern, general-purpose programming language. It's expressive, safe by design, and fast. It's also really fun to write. And you can develop it using a variety of tools. VS Code has great support for Swift, but you can use any number of editors like Vim or Emacs, which integrate with standard tooling like LSP. Swift is also cross-platform, supporting Apple's platforms, various Linux distributions, and Windows. It also scales from embedded systems right through to large-scale server applications. My colleagues, Kuba and Franz, gave talks about embedded Swift and Swift on Server at Apple's developer conference earlier this year. I'd recommend checking out their sessions if you want to learn more. We think that Swift is a great choice for server development, and we're using it at Apple for a range of services, including private cloud compute, which was announced earlier this year. Some of the reasons we think it's a great choice for server applications in particular are that it's fast and it has a low memory footprint, which is typically measured in megabytes. It has predictable performance, in part thanks to automatic reference counting. It also has advanced ownership features, which give you precise control over resources when you need it. There's also great interop with C++, so you can reuse existing libraries. Swift also has first-class support for concurrency built right into the language, making it easy to write scalable server applications. There's also a passionate and growing community with support for a variety of technologies, some of which are listed here. Let's take a quick look at Swift concurrency as it's so relevant to gRPC. Swift's concurrency uses async await. Functions which may suspend their execution are marked as async, and callers must await potential suspension points. You can iterate async sequences of values, much like a regular for loop. And task groups allow you to easily parallelize the execution of asynchronous work. This also highlights how Swift promotes structured concurrency to aid local reasoning. It's only once the work queue has drained and all of the child tasks have completed that the task group will return. It makes the lifetimes of resources clear and easy to reason about. Perhaps the best feature is that in Swift 6, the compiler can guarantee that concurrent programs are free of data races, eliminating a whole class of bugs. Very few languages have this level of protection, and those that do typically lack the ergonomics of Swift. We've spent the last 10 months redesigning gRPC for modern Swift. Let's take a step back and see how we arrived here. The project was started in 2017 by a Googler called Tim Burks. His approach was quite sensibly to wrap the gRPC core library and provide Swift APIs on top of that. This was done in conjunction with the open source community. When I joined Apple at the end of 2018, there was a desire to have a Swift library for gRPC, and ideally one written natively in Swift. My team had already created most of the pieces to do this. We'd recently released Swift Neo, which is a non-blocking event-driven networking framework with support for TLS and HTTP2. The open source community, and a developer called Daniel in particular, clocked onto this and had started working on a version of the library built on top of Swift Neo. We collaborated on this, eventually resulting in the release of the first version, which we're still using now. At this point, the Swift on Server community was still quite new, but having a way to easily interop with other services from Swift was a really big win for us. When we developed the first version, Swift didn't have a native concurrency model, and the library was built on top of Swift Neo's features and promises. It served us really well, but it's not modern idiomatic Swift, as this example highlights. I just want to note some syntax here because it might not be immediately obvious if you're unfamiliar with Swift. This method returns a feature of an event handling closure. The closure is highlighted here, and this is where the special syntax comes in. When a closure is the final parameter, the parentheses of the function can be dropped. So in practice, it looks more like this. This syntax is used quite frequently, and features later on, so just keep that in mind. When concurrency was introduced, we added async await flavors of the stubs, but these are just a thin veneer on top of the futures-based API and don't take full advantage of Swift's concurrency features. In a way, this made some things worse. A number of APIs couldn't be easily adapted, so some users ended up having to learn about two concurrency systems and how to glue them together. I can tell you firsthand that this is a fairly unpleasant experience. For the most part, though, it lowered the barrier to entry. Implementing services and using clients became much easier, which helped grow our user base. With that growth came more issues and more feature requests. And in a period of reflection, we started actively gathering feedback from users. What do they find difficult? What are they unhappy with? What features are they missing? We also asked about positive feedback. What are we doing well? What's easy to do that's difficult in other libraries? It's easy to just focus on issues and get a false perception that everything is bad. For the most part, our users were happy with what they had, but often just wanted more. Some of the things they were asking for were features available in other gRPC libraries, like hedging. Others were API gripes. The Interceptors API, for example, is very flexible, but it's still based on futures, which makes it difficult to use correctly. Gathering this feedback was really important. It allowed us to build up a picture of where users had difficulties and what we could do about them. We could see where we were and where we wanted to be, and this led us to a decision. Should we adapt the current library or rewrite it? Rewriting gives you the opportunity to fix a multitude of problems. However, I think it's important to note that doing a complete rewrite is a big decision. It's a large amount of work for which you also need to consider the opportunity cost. What else could we do if we didn't do a rewrite? You're also giving users a potentially large amount of migration work to do. The reward for them doing this has to really outweigh the cost. The new version can't just be better, it has to be significantly better. You also need to think about the support model. How long do you support the old version for? What about security patches? Do you have the capacity to support both? There's also risk involved. If resources get pulled for some reason, then you potentially have nothing to show for the work. The other option was adapting the existing library. For users, at least in the short term, this is probably more appealing because new features can be added iteratively without them needing to migrate. There's also inherently less risk. We already have the library. However, adding certain features would be difficult because of the current design. And some of the goals we had, like structured concurrency, aren't practical without effectively having a separate implementation anyway. And this was ultimately the impetus for doing a rewrite. Concurrency has fundamentally changed in Swift, and the nature of how we write concurrent programs is significantly different to when we wrote the first version. There are so many benefits to using Swift's native concurrency. Being a language feature is a force multiplier. Any concurrency-related improvements to the compiler, runtime, and language come for free. Tooling and diagnostics are also better. Swift has async backtraces, so debugging async code is just like debugging non-async code. You also get the benefit of familiarity. If you're familiar with Swift concurrency, then you don't have a new paradigm to learn. If you aren't, then you can learn about it from a much greater bank of resources than you could if you were learning about Neo's futures, for example. Having decided on a rewrite, we began embarking on our journey to a new major version. As the vision and designs at the core of the library, we wanted to be sure that we had a clear picture of what we wanted to build and the problems we were solving. Some of these were high level, and others were much more specific. We also have a set of guiding principles which we could draw back on when making design decisions and can do so in the future. One of the high-level goals was to make the library suitable for beginners and experts. The APIs should follow the Swift tenet that complexity should be progressively disclosed. This means it should be easy to pick up and use without having to learn lots of different concepts. You should be able to learn about more concepts as and when you're ready to do so. And this extends to the whole user experience. It should be easy to get started with the library, but the APIs should naturally extend to more complex cases as well. Another goal was for the library to feel familiar to users with experience of other gRPC libraries. Common features should be available and work like they do in other implementations and use the same terminology. We also wanted to make the library extensible. A mistake we made in the first version was baking in features which should have been made available via extension points. An example was assuming protobuf rather than having a pluggable serialization mechanism. This stopped users from self-serving as they had to ask us to add APIs, which increased the maintenance burden for us as we needed to maintain a duplicative set of APIs. To make sure we set off on the right course, we spent a lot of time designing and prototyping. The library has two types of component, runtime and compile time. The runtime part is what user code depends on. It has three broad layers: transport, call, and stub. The transport layer provides the long-lived communication between a client and a server. It doesn't know about protobuf or serialization. It just deals in streams of request and response parts. We provide two transports, an in-process one, which is useful for testing, and an HTTP2 transport built on top of Swift Neo. For the initial release, our aim with the HTTP2 transport is to provide the functionality that most users depend on, while leaving space to add more in the future. To name a few, the H2 transport supports pluggable name resolvers, servers config, and client-side load balancing, among others. This isn't a layer most users will need to touch beyond configuring which transport to use. The call layer sits on top of the transport and provides a way to execute RPCs. It handles serialization and deserialization. It knows how to do retries and hedging. It enforces deadlines, and so on. It can be used directly, but most users will just reach for the generated stubs instead. And that is, of course, the layer on the generated layer, which provides easy-to-use typed APIs. The compile time components are somewhat simpler and used ahead of time to generate the stubs. At the bottom, we have a code generation library, which is IDL agnostic, effectively providing a template for the generated code. On top of this, we have the Proto-C plugin, so you can generate stubs ahead of time. And on top of that is a Swift Package Manager build plugin. This allows you to generate stubs at compile time rather than having to manage code generation with separate tooling. Let's take a look at the stubs in more detail. One goal we had was to make it possible for you to have full control over the RPC. By that, I mean you should be able to access every part of a request and a response stream. You should be able to read and write the initial and trailing metadata. You should be able to send trailers-only responses, and so on. This should be done in such a way that the API makes it impossible for you to commit a protocol violation, like sending initial metadata after a message. This shouldn't make the common case of dealing with messages more difficult than it needs to, though. We also wanted the client and server stubs to feel similar and extend naturally to the interceptors API, minimizing the number of patterns that you need to learn about. To achieve this, we built a number of compiling but non-functional prototypes. As an example, this is a snippet of some non-functioning code for metadata. The details aren't important here, but what it allows you to do is try out the APIs. You can write code against them, even if you can't actually run it. It gives you a really great sense of whether the API is coherent and easy to use. You can also share it with others so that they can try it out and provide feedback. We created a number of different stub prototypes and iterated on the promising ones. Re-implementing existing services using the prototypes was also a very valuable exercise. One of the rejected options used the ownership modifiers to enforce the shape of the gRPC protocol. The idea was to encode a state machine across a set of related objects, each effectively representing a separate state. The various write methods would return new objects to transition between these states. And using the ownership modifiers stops users from taking an edge in the state machine that's no longer available to them. In this example, writing initial metadata consumes head and returns body. You can then write a message using body and finish it. Attempting to write another message isn't possible because body was consumed by the call to finish. The idea is quite neat and it does stop you from making protocol violations. But from a user perspective, it's not great. It doesn't feel at all idiomatic. In the end, we landed on stub APIs, which we think strike a great balance. They're easy to use while making it possible to access all parts of the request and response stream, while preventing you from making protocol violations. Importantly, they feel like idiomatic Swift APIs. Let's take a look at an example of the echo service. In Swift, a service stub is just a protocol, which is a similar concept to an interface in other languages. To implement the service, you need to conform a type to the generated protocol. Because the requirements are missing, the compiler emits an error and suggests a fix-it. Applying the fix-it generates the stubs for us. Let's focus in on the unary get method. It's straightforward. The input is a single server request, which holds the metadata and message. The return type is a single server response. No surprises here. And implementing it is as simple as you'd expect. Let's take a look at the bidirectional streaming update method. It looks a lot like the get method, but with a streaming request and response. To implement it, you return a response stream, which is initialized with the closure, allowing you to write messages back to the client. The closure iterates the sequence of request messages, writing back a reply for each one. It must also return metadata, which in this case is empty. This follows the shape of the gRPC protocol. Response streams end with trailing metadata and a status. In this case, the explicit return of metadata signals to gRPC that an OK status should be sent. If you encounter a problem while handling the request, then you can throw an error, to which you can also attach any metadata. gRPC will return this to the client as a status and trailers. Should you wish to reject the RPC, you can throw an error before the response, which results in the client receiving only a status and trailing metadata. On the client side, the stubs are similar. The unary get method takes a single client request as input and has a closure for processing the single client response. Any value returned from the closure is returned back to the caller once the RPC finishes. And the structure of the response passed to the closure follows the shape of the protocol. An accepted RPC has its message and both initial and trailing metadata, while a rejected RPC only has its error status and trailers. Most users won't need this granularity though, so you can just use the computed properties on the response to get what they need. You also aren't required to specify the request object and can just use the simpler API which builds it for you. And the stubs for methods with a single response also have a default response handling closure, which just returns the response message. And this is the API which the vast majority of users will reach for. Message in, message out. The story is similar for bidirectional streaming RPCs. You create a streaming request which takes a closure to write messages. You then pass that to the method, which has a response handler where you can access every part of the stream. Any value returned from the closure is returned to the caller when the RPC finishes, by which point the caller knows that any associated resources must have been cleared up. This is where structured concurrency shines. The lifetimes of the objects are clear and easy to reason about. Much like the unary example, most users don't need this level of granularity, and will just want the simplest API, which distills down to this: 2 closures, one for writing request messages and one for handling response messages. This final example shows how to set up a client with an HTTP2 transport and then make a request. First, we create the client and use an HTTP2 transport targeting an IPv4 address. We configure it with a default config and use the plaintext transport security. The client is run in the background with an async let. When the current scope exits, it will cancel the task running the client unless it's explicitly awaited. Running the client starts the transport, which will do name resolution, start an appropriate load balancer, and maintain any connections to the server. This will stop gracefully when instructed to, or more abruptly if the task is cancelled. We then create an echo stub wrapping the client, and make a request as you saw earlier. Hopefully this demonstrates how easy it is to get started with gRPC Swift. To recap, we rewrote gRPC Swift to take advantage of modern Swift. It has expressive, easy-to-use APIs, which are approachable for new users and extend to the complex use cases required by expert users. Swift's concurrency features have allowed us to design APIs which are easy to reason about and catch data races at compile time, making it easier for users to write correct concurrent gRPC applications. The library as a whole is also in a better place. It provides more standard features out of the box, including some we couldn't easily add to the first version. Finally, I'd like to mention some things we learned along the way. The first is that rewrites offer a great opportunity to fix a set of problems, but can bring with them a whole set of other problems, so make sure you're fixing the right problems and that the rewrite will stick. Perhaps unsurprisingly, rewrites are also a lot of work. We spent a lot of time upfront prototyping, designing, and planning, which I think has paid off, but time will be the real test. Having a set of principles to guide the project has also been great. If we were unsure in our approach, then referring back to these often made things clearer. We also learned that having non-functional prototypes so you and others can try out the APIs is incredibly valuable, doubly so if you apply them to existing use cases. Different perspectives help a lot, so getting feedback from collaborators and users early in the process was also really helpful. Incremental milestones and goals have also been great. Having something to aim towards helped us remain focused, and having goals which lend themselves to demos helped us to get targeted feedback along the way. So what's next? We still have some development work left to do, but we plan on tagging an alpha release soon after Swift 6 is released. And our aim is to tag V2 early next year. We're also looking for feedback, so please try out the library. The project is on GitHub, where you'll find a Getting Started guide for V2. And with that, I'd like to thank you for your attention.
So very nice API. So in your one of the first slides, you mentioned there are so many disadvantages of a rewrite. So one of them was, I think, migration. So have you thought about the migration story and any tooling or other thoughts around it?
Yeah, thank you. It's a great question. We have thought a little bit about migration. We need to write down our plan, but our current thinking is that V2 will exist in source with V1 for a while, so that you can migrate services sort of one at a time. This is a little bit unfortunate, but that's just the way it's going to be. And then we think over time we're probably going to sort of phase that out and effectively remove V1 from that branch. So there'll be a time where you can have sort of both V1 and V2 running at the same time, but that will really just be to migrate to V2. In terms of tooling, we haven't looked into this yet. I think generally it might be quite difficult to do in sort of in a way that covers all bases. Part of this is simply because you have to move to a more structured approach. So I think that's difficult to do with tooling.
Hi, thanks.
Hey, Tim.
So how do you build this? I mean, I recalled there were just multiple different ways. There used to be CocoaPods. And I guess the question is, how are you building it, and how are Swift gRPC users doing their builds?
Just with the Swift package manager. CocoaPods is sort of slowly being phased out. Lots of packages are no longer supporting it. Everyone's really coalescing around Swift package
So I guess
manager.
other things might be Bazel or Xcode.
Yeah, so Xcode has support for Swift PM sort of directly, so you can open a Swift package in Xcode and you can include that as part of your Xcode project. There is some support for Swift in Bazel. I'm not sure how mature that is. I haven't used that personally.
Thanks. And then one last thing is, if I wanted to build something with Swift and run it in a container, are there examples that I could look to? Are there any known problems with doing container builds and running them? Like distributions that are best, like, will this work with Arch or various embedded Linuxes?
Good question. There have previously been issues in the past. I think these have all been resolved now, so I don't think there are currently any issues to doing this. I also don't think we have any examples at the moment of how to do this. Maybe we should add some to the repository. I guess that's something to do. But it should just be a normal sort of standard flow. There's nothing exciting there, I think.
Yeah, I think it would be a general Swift issue, like some glib dependency or something that Swift has that might mismatch what's in the distributions.
That's true. There are a bunch of different containers for Swift targeting different distributions. There are also sort of slim versions of these images as well, so you can copy your binary over.
Hi, thank you very much for the talk. So I know you primarily was thinking about the server use case, but I'm wondering also about the potentially mobile use as well. So I wonder if you have any knowledge on the existing adoption of the V1 library, because when I searched Google, I saw some people are using it for mobile as well. and how the V2 compared to that in terms of usability on mobile, and have you given any thought about mobile adoption?
That's a great question. We haven't given any special thought to mobile adoption. So SwiftNeo, which underpins our HTTP2 transport, there's a version of that which is built on top of Apple's network framework rather than using sockets directly. So that certainly works better on iOS and so on. I think there are some other things we can do to improve the support for this. So there are things that Network Framework offers that we don't necessarily take full advantage of yet. So this is perhaps something we also need to look into a little bit more.
Thank you. But just to clarify, would the new library work on mobile?
Yes,
it's
yes,
just not,
of course. Yeah.
may not be optimized. Is what
That's correct, yeah. Okay. So it should work just like the current version does. It has, you know, a similar set of dependencies. Great. All right, thank you very much.